Hello everyone and welcome. Today we're going to tackle a really cool and super practical application of derivatives, the rate of change of quantities. Trust me, this is where calculus stops being just about formulas and starts feeling like a real-world superpower. So let's get right into it.
So just imagine this. You upload a new reel to Instagram and it starts blowing up. The view count is just shooting up like a rocket. Now, if your friend asks, hey, how fast are the views increasing at this very second? What would you say? I'm not talking about the average views per hour. I mean the speed of the view count right now at this exact instant. How on earth do you measure that?
Well, guess what? That exact question is precisely what calculus was designed to answer. The special tool we use for this is called the rate of change, and it allows us to measure the speed of pretty much anything, from a viral video to a growing economy, at any single moment. Okay, so what is this rate of change, really? The easiest way to think about it is like this. The derivative is your personal speedometer, but not just for a car. It's a speedometer for literally anything that changes. It tells you exactly how fast something is happening at one specific point in time. Now let's look at the official definition. When we write dy by dx, we're not just writing some random letters. We're asking a very specific question. How fast is the quantity y changing for every tiny, tiny change in the quantity x? The answer it gives us is the instantaneous rate of change, which is just a fancy way of saying the speed at that exact moment.
You know, to make this crystal clear, let's compare instantaneous rate with average rate. The instantaneous rate, our dy dx, is like looking at your car's speedometer. It tells you your speed is exactly 60 kilometers per hour times right now. But the average rate is like saying, oh, I drove 100 kilometers in 2 hours, so my average speed was 50. Both are useful, for sure, but only the derivative gives you that right now speed.
All right, ready to put this speedometer to use? Let's start with level 1 problems. These are the most direct type, where one thing changes simply because another thing changes. And don't worry, it is much, much easier than it sounds. So for any level 1 problem, you just need to follow this simple 4-step recipe. First, find the formula that connects the two things. Second, you differentiate. Third, you plug in the value you are given. And fourth, you state your final answer with the correct units. That's it. Let's try it with a problem. Imagine a meme is so funny, it's going viral in a perfect circle, like a blast wave. We want to figure out how fast is the area of this meme's influence increasing at the exact moment its radius reaches 10 centimeters. Okay, step 1 is super simple. What's the formula that connects the area, A, and the radius, R? Of course, it's the area of a circle. A equals pi r squared. Now for step 2, the calculus part. The question asks for the rate of change of area with respect to the radius. That phrase, with respect to, is our signal. It's telling us to find dA over dr. So we differentiate A equals pi r squared with respect to r, and we get dA over dr equals 2 pi r. And finally, we combine steps 3 and 4. The problem tells us the radius is 10 centimeters. We just plug this value into our derivative. So dA over dr becomes 2 times pi times 10, which is 20 pi. This means at that exact instant, the area of the meme's influence is growing at a rate of 20 pi square centimeters for every centimeter the radius increases. See? Not so bad, right? Okay, level 1 is done. Great job. Now let's level up. We'll call this section the domino effect. This is where things get really cool, because now we have quantities that are connected through a third party, which is usually time. So the secret behind this domino effect is a super powerful tool you already know, the chain rule. Think about it. If one thing changes with time, that causes a second thing to change, which then causes a third thing to change. It's a chain reaction. The chain rule lets us connect the speed of the first change to the speed of the last one. It's brilliant. And just like before, we have a clear game plan. This time, it's 5 steps. First, you list out everything you know. Second, you find the main formula. Now, the most important step is number 3. You differentiate the entire equation with respect to time, t. After that, you just plug in your numbers and solve. Now listen very carefully. This is super, super important. A lot of students fall into this trap. They see a number in the question, like x equals 10, and they get excited and plug it into the formula right away. Please, don't do that. You must always differentiate the general formula first, and only then can you substitute the numbers. This is the golden rule here. Remember it. Okay, time for a level 2 problem.
Imagine you're playing a game and you find a magic item that expands your inventory space, which happens to be a perfect cube. Its volume is growing steadily at 9 cubic centimeters per second. The question is, how fast is the surface area of the inventory growing at the exact moment one of its edges is 10 centimeters long? Let's start with steps 1 and 2, listing our variables and formulas. We'll let x be the length of the cube's edge. So the volume, v, is x cubed. And the surface area, S, is 6 times x squared. And of course, everything is changing with respect to time, t. And now for the crucial step 3. We have to differentiate both formulas with respect to time. Using the chain rule, v equals x cubed becomes dv dt equals 3x squared times dx dt. And s equals 6x squared becomes ds dt equals 12x times dx dt. Do you see it? That dx dt has appeared in both equations. That's our domino, our connecting link. Okay, time to plug in what we know. We have dv dt, which is 9, and we have x, which is 10. Let's use the volume formula first to find our missing link, dx dt. So 9 equals 3 times 10 squared times dx dt. This means 9 equals 300 times dx dt. A little bit of solving, and we find that dx dt is 3 over 100. Perfect, now we have the link. We can take this value and plug it into our surface area equation. So ds dt equals 12 times 10 times our new value of 3 over 100. And when we do that calculation, we get our final answer, 3.6 square centimeters per second. That's how fast the surface area of your inventory is growing. You are doing great. Awesome job. We've made it through both levels of problems. So before we finish, let's just do a quick recap of the key ideas you need to remember. First, always remember that the derivative is your calculus speedometer. It measures speed at an instant. Second, for related problems, think of the domino effect and use the chain rule. Third, and I'll say it one more time, the golden rule. Differentiate first, then substitute. And finally, a small point, but if you ever get a negative answer, don't panic. It just means the quantity is decreasing instead of increasing. And that is pretty much it. You have just learned one of the most powerful and useful concepts in all of calculus. From tracking social media trends to understanding physics, you now have the tools to measure how fast the world is changing all around you. You have absolutely got this. So, I'll leave you with this final thought. Now that you have this powerful calculus speedometer, what will you measure? Maybe the growth rate of your favorite YouTuber, or how quickly a new fashion trend is spreading. The possibilities are really endless.